Hey there, this is part 2 of our video for Fundamental Theorem of Calculus. So we're going to continue. In the first video we did the Fundamental Theorem of Calculus part 1, and now we're going to move on to the Fundamental Theorem of Calculus part 2. So first let's practice finding the antiderivative of something like this. So the integral notation is also used to find the antiderivative. So what this tells us is you can also think of it as the derivative of some function is 3 plus x squared over x. So this is the derivative of some function, and when we see the dx here, that means that the derivative was taken with respect to x. So this is with respect to the variable x. And so then we want to find f of x, right? So this is the derivative of some function, and the derivative was taken with respect to x. So one of the things that we can do then is simplify. So I'm going to multiply the numerator out. So that will be 9 plus 6x plus x squared dx. And now I can use we can use our techniques of separating the denominator, right? So I can say this is 9 over x plus 6x over x will just give me 6 plus x squared over x is just x dx. And so now this is the derivative of some function, and I want to find the antiderivative. So where did it come from? So this is 9 natural log absolute value of x plus 6x plus x squared over 2, and then plus a constant. When we take the antiderivative, we always add plus c at the end. So this will be our antiderivative. And so the question then arises as to, okay, so if this symbol, the integral, means antiderivative, but as we saw in the prior sections, is that the integral also means the area under the curve. So what is the connection? What's the connection between antiderivative and area under the curve? And so that's what the Fundamental Theorem of Calculus part 2 comes and makes that connection. So the Fundamental Theorem part 2, what it says is that if you have the integral, the definite integral, the integral from a to b of some function f of x dx, then this is equal to capital F of b minus capital F of a. So you have your f of b minus f of a, where capital F of x is the antiderivative of little f of x. So this is the Fundamental Theorem of Calculus part 2. So let's prove why is this true. So let's have a discussion. Why is this true? How does it work? So we're going to start with recalling some of the information that we used for the first Fundamental Theorem of Calculus. So recall that we had the integral from a to x of f of t dt gave us the area under the curve from a to x. And also that when I take the derivatives, let me say, and when we take the derivative of this function, the integral from a to x of f of t dt, we get f of x. Right? This is our Fundamental Theorem of Calculus part 1. So we've abbreviated FTC 1. This one, Fundamental Theorem of Calculus part 2, is usually abbreviated FTC 2. And we technically need the FTC 1 in order to prove FTC 2. So what does this mean? This really means that when you have the integral from a to x of f of t dt, you really end up with capital F of x plus c. So we're going to define it this way, where the derivative of f, right, the capital F, is the little f. So that's essentially what this says. So when I take the derivative of this, I get little f. So f is the antiderivative of little f. And we're going to use this function to show then how do we get f of b minus f of a. So this is the crux of the matter. This is the big thing. The reason that it's called the fundamental theorem of calculus. How do we make the connection between the area under the curve and this capital F, which is the antiderivative of little f of x? So let's start by letting in this function let x equal a. So when x is equal to a, what we get is that the area then becomes the integral from a to a. So the area between a and a of f of t dt is going to be, according to this, f of a plus c, right? Because this is some antiderivative. So it's going to be f of x, capital F of x plus c. So this, I'm replacing the x with a. And so that arrow was not doing what I wanted it to do. Okay, so we're replacing the x with a, so then this x will be replaced with a, so I get this much. But what does this mean, right? The integral, the area between a and a, well, if we look at the area between a and a, right, that means that the delta x is a minus a over n, but that's just 0. So this area is just 0. The area between a and a, there's nothing there. It's just a line segment. So there's no area. So that what that tells me then is that 0 is equal to f of a plus c. So this tells me, solve for c, c is equal to negative capital F of a, where again capital F is the antiderivative of little f. So that's how we're defining it. And let me just go back to that. Why are we defining this as the antiderivative? Well, because the derivative, we're saying the derivative of this integral just gives us the little f again. So that means that this little f is the derivative of some function. So that's the capital F of f, the antiderivative. I don't know if that made any more sense. All right, so now let's go to what if x, so using our same integral, right? We know that the area under the curve is the integral from a to x of f of t dt. Now, let's let x equal b. So if we're on the interval a to b, then what does that become? So when x is b, this is going to be the integral from a to b of f of t dt. But what does that equal? From the FTC part 1, where we know that the integral from a to x of f of t dt is equal to capital F of x plus c, where capital F is the antiderivative. So this is going to be capital F of b plus c. But we're using the same function on the same interval, so we already know then that c is equal to negative f of a. So let's use that here. So I can say then the integral from a to b of f of t dt is equal to f of b minus f of a. And so this is our FTC part 2. So in general, what we can then say is that we can just adjust our variable. And so we can say that the integral from a to b of f of x dx is equal to f of b minus f of a, right? Where f of x, capital F of x, is the antiderivative of little f of x. And so we can say this in general. So this is our FTC part 2. So let's look at our example and make the connection between how is this helpful, because this is going to be what we use the most instead of you doing the Riemann sums. So let's find the area from on the interval 1 to 4 of quantity 2 plus x squared in two ways. We're going to use the definition of the definite integral first using Riemann sums, and then we're going to use the FTC part 2 to see if we get the same thing. We should get the same thing, but just to appreciate the two methods, mainly to appreciate the second method, because that would be the shorter one. Okay, so if we want to find the area, so using part A, I know that the integral from 1 to 4 of 2 plus x quantity squared dx is going to be equal to the limit as n goes to infinity of the summation I equals 1 to n of delta x times f of x of I star. That's how we convert an integral to a Riemann sum. So what are some of the things that we need to find? We need to find delta x, and we need to find our x of I star. We are not told here which endpoint to use for the height of each of the rectangles. So when you're not given which one to use, let's always choose the right one, just because that's the easiest one to evaluate, which is a plus I delta x. So let's find our delta x. So delta x we know is b minus a over n. So in this case, 4 minus 1 over n, which is 3 over n. So that's our delta x. And you can just, if you're comfortable writing what your x of I star is, which is your right endpoint, then a, what's a? A is 1, so it'll be 1 plus I delta x, so 3i over n. So that's one way, is by memorizing that. The other way is to break up your interval. So you know you have 1 to 4, and then you're going to have n rectangles in there. So start drawing your rectangles. So first rectangle, second rectangles. I haven't drawn the function, so I'm not quite sure exactly if it's increasing or decreasing, but I'm just drawing myself some random rectangles, right? And the main goal is to arrive at the ith rectangle, so I can see which one am I using. So each time you're adding 3 over n is the base, because that's our delta x. So this will be 1 plus 3 over n, then 1 plus 3 over n plus 3 over n, so 2 of those, and then 1 plus 3 times 3 over n, and so on until you get to the ith rectangle will be 1 plus I times 3 over n. That will be the right endpoint, and then if you were using the left endpoint, it will be I minus 1. So that's another way to get to your right endpoint. So either way, memorize that or break up your number line. And so now, what's our function? So we have our delta x, we have our x of I star, so we need f of x. F of x is 2 plus x quantity squared. So now we're ready to plug it into the Riemann sum. So then that Riemann sum then is going to look like the limit as n goes to infinity of summation I equals 1 to n of delta x is 3 over n, times f of x of I star. So f of x of I star, we're using the right endpoint, which is 1 plus 3i over n. So f of 1 plus 3i over n. And so let's see what that is with our function. So I'm going to do it over here to gain more space. So I'm going to have the area is the limit as n goes to infinity, summation I equals 1 to n, my delta x 3 over n times f of 1 plus 3 over n. Here's my f, 2 plus x quantity squared. So this will be, let's use brackets here, 2 plus x, this is what I'm plugging in for x. So 2 plus 1 plus 3i over n, and then the whole thing is square. So that's my f of x of I. And then what do I do from here? What is the goal? So remind yourself, what is the goal? The goal is to be able to use the formulas. So remind yourself what those formulas are. And the goal is to try to use these formulas to simplify. And so here, Let's simplify. So 2 plus 1 is 3. I'm going to have what? 3 plus 3i over n quantity squared. So we should probably multiply that out because I want to be able to identify summation of a constant, summation of summation of I squared. I don't think we're going to get the I cube in here, so I don't need to worry about remembering that one right now. So let's see, what does this become? So I still have my 3 over n times, let's multiply that out. So it'll be 9 plus, what's that, 9, and then double that, so 18 I over n, double check my math there, I hope I did that right, plus 9i squared over n squared. And then distribute the 3 over n in to simplify. And then hopefully we'll be able to use our formulas. Right? The goal when you're simplifying this, when you get to this part, is like, okay, what do I do? Well, what is the goal? The goal is to try to get rid of the summations and the i's. So we want to be able to use these formulas. Those formulas are giving us the sum already. So distribute that in. So I'm going to get 27 over n plus 18 times 3. What is that? So we get 54 I over n times n is n squared, and then the last one, 3 times 9, so 27 I squared over n times n squared is n cubed. So this is my sum, and now we can split them up, and keeping in mind that our goal is to use these guys. So split up the sums. I have my limit as n goes to infinity. I haven't taken any limit, so I have to keep writing the limit. So I'm going to have I equals 1 to n of 27 over n plus summation I equals 1 to n of, and I'm going to try to separate the constant from the I, and then plus summation I equals 1 to n of 27 over n cubed. Again, separate the constant from the I. And so I'm taking this limit, and now, right, there's no I in here, so this is our constant. So I get to use this one. So it's n times c. So n times 27 over n is just going to be 27. So I'm going to have the limit as n goes to infinity. I am not taking the limit yet, right? So I'm just evaluating the summation. So this is just going to be 27 plus, and then this is my constant, 54 over n squared, and then times the summation of the i's. So that's n times n plus 1 over 2 plus 27 over n cubed is my constant, and then the summation of I squared is n times n plus 1 times 2n plus 1 over 6. When you use this in math, you just tend to memorize them. Okay, can we simplify or can we take the limit? If you can take the limit from where you are, then that's great. If you need to simplify a little more, simplify a little more. Sometimes it's harder to see what the limit is when you still have all the things in there. So let's see. 54 divided by 2, that gives me 27, and I can perhaps maybe get rid of one of the n squares. So cancel that one n, or you can leave it and just notice that that's going to be n squared and that's going to be n squared on the bottom. But I already canceled this, so I'm just going to say 27 times n plus 1 over n, right? I cancel that n with one of those n squares. Plus, and then here I can cancel that one n with one of those, so I'm going to have n squared on the bottom. And is it worth simplifying that? Let's see, I'm just going to leave it as 27 over 6, and then we'll have n plus 1 times 2n plus 1, and then 6n squared. And now we can take the limit. As n goes to infinity, this is going to be 27. I don't need the limit anymore because I am taking the limit. So there's no n there, so that just stays 27. And then what happens with the other ones? So let's look at the powers. Power in the numerator, highest power is n to the first, and then n to the first, so that's good. just going to be 27 again. And then what about here? Highest power is going to be n squared. I have n times 2n. So here I'm going to get my highest power, and it's going to be my highest term, I should say, is going to be 2n squared plus stuff, right? If I multiply this out, but the highest one is n squared and n squared. So I'm going to get the ratio of the coefficients. Here I have to be careful because when I multiply these out, I can't ignore that 2. I get n times 2n, so it's 2n squared. So when I look at the coefficients, I have to take that 2 into account with that 27. So I'm going to be left with my coefficient is going to be 27 times 2, and the coefficient on the bottom is just 6. And so what are we left with? So add those up, and that will be our answer. I get 27 plus 27 plus 9, which is 63. So that will be the area. Phew! So that was part 1. So that was just doing the integral using the definition of the definite integral. Now, part B, enter FTC part 2, the fundamental theorem of calculus that makes the connection that the antiderivative is related to the integral. So part B is using FTC 2, which says that the integral from a to b of f of x dx is f of b minus f of a, right, where f of x is the antiderivative of little f of x. Antiderivative of little f, meaning that f prime, capital F prime, is equal to little f. All right, so then we want to know the integral from 1 to 4 of, what was our function, 2 plus x quantity squared dx. So I just need to do then is find the antiderivative of this and then plug in into the antiderivative the top limit, so 4, minus the bottom limit, 1. So this is going to be f of 4 minus f of 1. I always think of it as top minus bottom. So our goal then is find f of x, the antiderivative, which we know how to do. How do we find the antiderivative of this? We can multiply it out. So when you multiply it out, 2 plus x quantity squared, that's 4, plus 4x plus x squared dx, right? And then do the antiderivative of that. Oops, when we're doing the antiderivative, you no longer need the integral there. So the antiderivative of 4 is 4x, and the antiderivative of 4x is going to be 4x squared over 2. So 2x squared plus x cubed over 3, just using the general power rule. So this is my antiderivative. Usually we have a plus c, but this is a definite integral, so we don't need the plus c. If you add it, if you do plus c, you'll just see that when you plug in b and a, you're going to have plus c and then minus c, so they'll just cancel anyway, so we don't need it. And so now let's do the way that you usually say you're going to plug in the a and your b is you're going to plug in your 1 and your 4, with starting with the 4 first, right? So then when you do f of 4 minus f of 1, that's what this notation kind of means. So plug in the 4 first, so it's going to be 4 times 4 plus 2 times 4 squared plus 4 cubed over 3 minus, plug in the 1. So use parentheses. So it'll be 4 plus 2 plus 1/3. So make sure that you use parentheses. Don't just do minus because you might forget to then distribute it. And let's compute this out. And what is this? 4 plus 2 is 6 plus 1/3. So it'll be minus 6 minus 1/3. So combining this, I'm going to get 48 plus, well, let's combine the things that are not fractions. So 16 plus 32 is 48, minus 6, that's 42. So I'm going to have 42 plus 64 thirds minus 1/3 gives you 63 thirds, which is 21. So you really have 42 plus 21, which is 63. The same thing we got before using the Riemann sums. But the Riemann sum definition of the area takes a really long time versus the fundamental theorem of calculus part 2 makes it really nice. It just tells us, oh, when you evaluate the area under the curve, between the curve and the x-axis on an interval, really all you need to do is find the antiderivative of that function and then evaluate it from the top limit minus the bottom limit. So the fundamental theorem of calculus is really nice in that way because we no longer have to do Riemann sums to find the exact area. All we have to do is find the antiderivative, which we know how to do. And so it's much, much faster. Let's try another example. So let's evaluate the integral from 1 to 3. And notice then that as functions start to become more complicated, the Riemann sum on this will be a lot harder to do, right? And even if we had assigned our formulas that we studied, that we said our goal is to try to get these formulas, we don't have one for natural log or for sine or for cosine. So this will become a lot harder to do without the fundamental theorem of calculus. So here, let's evaluate this, and we're going to use the fundamental theorem of calculus, so FTC 2. So what that means is then I'm going to just find the antiderivative. So can I just find the antiderivative of this? Yes. So I'm going to say the integral from 1 to 3, so the area between this curve and the x-axis on the interval 1 to 3 is going to be the antiderivative of this function evaluated at 3 minus the antiderivative of that function evaluated at 1. So let's see what we get. So let's find the antiderivative. So this is going to be the antiderivative of x squared is x cubed over 3 minus antiderivative of 5x, use the general power rule, plus, and here the antiderivative of 1 over x, don't use the general power rule. This is, you should recognize this 1 over x as the derivative of natural log. So that means this antiderivative then is the natural log of absolute value of x. And then we need to evaluate it from 1 to 3. Plugging in the top limit first so that we get f of 3. So then this becomes 3 cubed, which is 27 over 3 minus 5 times 3 squared, so 5 times 9, so 45 over 2, plus natural log of absolute value of positive 3 is 3, and then minus, and here don't forget your parentheses because you have 3 terms, so plug in the 1, so 1/3 minus 5/2 plus natural log of 1, which is 0. And so that one will just go away, but you can combine the terms that are the same, right? So I have 27 thirds minus 1/3 will be 26 thirds minus 45 over 2 minus a minus, so plus, so that will become a plus 5/2, so negative 45 over 2 plus 5/2 will be minus 40 over 2, and then plus the natural log of 3. So 26 over 3 minus 20 plus natural log of 3. You can get a common denominator here and make things easier or prettier. So common denominator will be 3, so that will be negative 60, and so you can simplify further and to get a more exact answer. But notice how much faster this is using FTC 2 than trying to use a Riemann sum. And the last example, let's try the difference between a definite and an indefinite integral. So what is the difference between a and b here? So if I have just the integral of sine x plus 2 to the x minus 1 over 1 plus x squared. And I have this integral. So a is called an indefinite integral. And what is this asking you for? And versus this one is a definite integral. And what is that one asking you for? Right in here, we just want the antiderivative. We just want the antiderivative of the function. So what this is telling us is that the thing in parentheses, that is the derivative of some function, and the derivative was taken with respect to the variable x. What this one is asking us to find is we want the area between the curve and the x-axis. So they look very similar, but they're asking us different things. This one just wants the antiderivative, and this one wants an area. So one should be a function, and the other one should be a number. So for A, I just want the antiderivative. So my antiderivative here, what's the antiderivative of sine? That would be negative cosine x, right? The derivative of cosine is negative sign. You can check it. So it would be negative and negative, give us a positive. Plus, what about the antiderivative of 2 to the x? You always get the exponential back, but this, the base is not e, so I have to divide by the natural log of 2, and then minus the antiderivative of this. So what function has a derivative of 1 over 1 plus x squared? Inverse tangent. So that's inverse tangent of x, and then plus c. So an antiderivative, you get plus that constant. And so now for part B, let me copy that. This is asking us for an area. So using FTC 2, I still need to find the antiderivative, which luckily I already have for part A. So, but what this is asking us is find f of 1 minus f of 0 for this, by finding the antiderivative, which we did in part A. So then this is going to be negative cosine x plus 2 to the x over ln of 2 minus inverse tangent of x, and I'm evaluating it from 0 to 1, top minus bottom. Always plug in the top limit first. So this is minus cosine of 1 plus 2 to the 1 over the natural log of 2 minus inverse tangent of 1, and then minus parentheses because you're about to plug in 0. So negative cosine of 0 plus 2 to the 0 over natural log of 2, that's a 0, minus inverse tangent of 0. Right, so this is my capital F of 1, and this is my capital F of 0, FTC 2. And then the last thing to do is just simplify those. 1 is not a particular radian angle that we know, so you can just leave it as negative cosine of 1 plus 2 over ln of 2. Inverse tangent of 1, we do know what that is, or we should know, that's pi over 4, minus cosine of 0, we do know that cosine of 0 is 1, so this will be negative 1, so minus and minus becomes plus 1. Let's take that negative in. And so then we're going to have, so plus 1 and 2 to the 0 is 1 over ln of 2, so minus 2, minus 1 over ln of 2. And then minus and minus is plus, but inverse tangent of 0 is 0. So we can just, let's see, can we combine anything? Not very well, right? So negative cosine of 1, we can combine the only like terms I see are my ln of 2 over ln of 2 minus 1 ln of 2 will give us 1, but then nothing else are like terms. So we're going to have plus 1 over ln of 2 minus pi over 4 plus 1. And there's not much you can do with this other than put in a calculator and get a decimal answer. And if that's what you're asked in your homework, just pay attention to how many decimal places you're going to want. For me, on a quiz or a test, I prefer the answer exact like this. Okay, so hopefully this gives you an idea and an appreciation for the fundamental theorem of calculus. There's a reason that is called the fundamental theorem of calculus, because it is such a cool theorem, and as you can see, it just saves so much work, like having to do those Riemann sums. I'm sure you have not appreciated having to do those Riemann sums. They're kind of fun. But they can be tedious and they can be confusing. And if you make a little tiny algebra mistake, the whole thing is ruined. And the fundamental theorem of calculus comes in and makes that very important connection of the antiderivative and the area between the curve and the x-axis, and it allows us to then find the area by computing the antiderivative. And I just hope that you can see and appreciate how incredibly powerful this theorem is and how cool it is. And whoever developed it, I'm sure, for those of us that like history of math, you can look up how it was developed and how it came to be. But it's just one of those things that is just absolutely fascinating, and it is so helpful from here on out in the study of calculus. So anyway, I hope that get comfortable using the fundamental theorem of calculus. It will be from now on in everything you do in calculus. Calc 2, you'll use it all the time, and in Calc 3, and in differential equations. So it's just a really, really, really important development in calculus. So, well, I'll end there because my video now is way too long anyway, but email me if you have any questions.